Okay, before we start, I want to make sure that everyone prepare your topic first. Then I'm going to pass this paper with the pen. So don't forget to pass the pen along with the paper. You should write your name below the topic title that you want to do for the first project. Okay? So if you want to group with certain specific person, then write their names all together and then circle it so that I can know that you guys want to be in the same group. Okay, so I'm going to pass this paper and then collect at the end of the class. We're not going to finalize the group today. It's just I want to know your preference first. Okay. So any question about the project or yes, do you have a question? Maximum is 6. Minimum is 4 or 3. So 3 to 6. But if I see too many groups of 3, then I might add some more people on it to make it group of 4. Any other questions? Okay. So next week we have a holiday. So I want to cover 3 slides in 2 days in this week. So I want to go a little bit faster. So let's talk about series. So we talked about sequence last time. What is a series? So series is basically a sum of sequence. So if the sequence is finite sequence, you're just summing up finite numbers. But if it's an infinite sequence, then you have to sum infinitely many numbers. So basically, a series is not a number, it's a limit. It's a limit of partial sum. So if you take the first n numbers from the sequence and you sum them up, that's your partial sum. And when you take the index to increase up to infinity, then it's your series. So series is a limit, not a number. If the limit exists, then you can say series converges to a certain number. But if it diverges, if the limit doesn't exist, then you should say series diverges. So for example, you can say that this 1 over 2, 1 over 4, 1 over 8 sequence make up a series of this one. And obviously, if you're looking at this picture here, it always, it doesn't go increase infinity. It always, each sequence, each term in the sequence takes a portion of this big square of side 1. So you can imagine that this series converges to 1. So we're going to talk about the convergence and divergence of the series for this slide and then apply it to the power series in the next slide. So talk about the divergence. How do we know that this series, 1 plus 1 over 2 plus 1 over 3 up to infinity, is diverging? So easiest way is just compute the final partial sum for some indices. For example, if you take the index 1 up to 4, then you can see that the partial sum is increasing a little by little. But if you look at the sequence, the term of the sequence, the increment of each partial sum is decreasing. So you don't really get the concrete evidence that this series converge or diverge. So instead, if you increase your index exponentially, 10, 100, 10,000, and so on, then now you can see that the series actually increasing in a constant speed. So then you can guess that this series might diverge, which means that you can make your partial sum as big as you want by adding larger and larger number of summands. So you can actually prove the divergence by this way. So for example, if you have S4 adding 4 terms here, you can group the last two to make it into 2 times of 1 over 4. So it's basically 1 times 3, 1 plus 2 times 1 over 2. And if you add first 8 terms, then you can group the last 4 to make it into 1 over 2, bigger than 1 over 2. So you can consider that S8 is bigger than 1 plus 3 times 1 over 2. So you can see that this number, 2 and 3, are the exponent of your index to the power of 2, and S is 2 to the power of 3. So if you want your partial sum as big as you want, then you can increase this number, and the way you can make your partial sum greater than that number is taking that number, the 3 or 2, as an exponent of your 2 in the index. So you can see that it can be as big as you want. Now, there are special types of series. We're going to go through these. One type is alternating series, which means that your number, the summand, changes the sign. And it's positive next, negative, and positive next, and so on. So if you have such sequence, sometimes it converges, sometimes diverges. But for example, let's see, 1 minus 1 over 2 plus 1 over 3, 1 over 4. So if you keep doing this, adding these number, it converges to certain number and actually converges to log of 2. So log of 2 is actually same as ln 2 if you're using ln. But from now on, we're not going to use ln. Instead, we're going to denote it as log. Anyway, so if I plot the partial sum as a sequence and plot the value of sequence as in xy plane, this is how it oscillates. So first S1 is here, and then you're subtracting 1 over 2, so it's going down by here, and then adding 1 over 3, you go up by this, and down, up, down. But every time, if you want to get the next partial sum, the increment or decrement is the amplitude of that increment and decrement are decreasing, right? So eventually you can imagine that it goes to converge at certain level. So that's why you can imagine that this is converging. And let's talk about the special type of convergence. If your series converges even after take all the summands as an absolute value of original value, then it's called absolute convergence. So for example, look at this one. So if I take the absolute value of the summand and take that as a series, so 1 over n squared, this also converges. So basically I think it converges to pi over 6 or pi squared over 6. So anyway, it converges. So however, if you take this series and then take the series of absolute value, we already saw that this diverges. So if the absolute value, the series of absolute value converges, then it's called absolute convergence. But original series converges, but the absolute value series does not converge, then it's called conditional convergence. So both converges, but there are the speed of convergence are different. The first one, this 1 over n squared, the alternating series of 1 over n squared converges way faster than series of 1 over n, alternating series of 1 over n. Okay, so this is 1 over n squared, this is 1 over n. Okay. Now let's talk about some tests that you can apply to determine the convergence and divergence of series. So first test you have to apply is whether your sum ends goes to 0. If it's not goes to 0, then your series definitely diverge. So for example, let's look at this one. So your an is 1 plus 1 over n to the power of minus n, which means that it's 1 over 1 plus 1 over n to the power of n. The limit of an is 1 over e. E is the natural constant. It's not 0. So if it's not going to 0, going to converge to 0, then when you take this as a sum end infinitely many times, you're adding up small number infinitely many times. No matter how small that value is, if you keep adding those small numbers, you can make it into as large as you want. So therefore, it diverges. So another test that you can apply is alternating series test. If you have an alternating series and you definitely know that your absolute value, an, converges to 0, then your alternating series converges. So you have to be careful about taking nth term test and alternating series test. Nth term test applies to any series. Alternating series test only applies to alternating series. Oh, by the way, so what happens to this minus 1 n here? So n from 1 to infinity. So this is obviously alternating series. And if you take an part in this format, an is 1 over n, and it goes to 0. So therefore, you can conclude that this alternating series converges. Okay. Okay, there are other tests. Geometric series test says that if your common ratio r has an absolute value less than 1, then it converges. If it's bigger than 1, it diverges. So basically, it's a well-known. If you remember the formula for the alternating geometric series sum, so if you have a finite sum of geometric series, ar n here, so it's a times 1 over r, 1 minus r, k plus 1. So you can imagine, although it's not a proof, but just convince yourself why this test makes sense. If r is less than 1, then this term goes to 0. So therefore, you have a convergence. But if r has an absolute value bigger than 1, then this might diverge. So you have no value that corresponds to this when k goes to infinity. And another test is p-series test. So if you have a series of this form, depending on the exponent value, p, it converges or diverges. So if p is bigger than 1, it converges. For example, if you have 1 over n squared, it converges because p is 2, which is bigger than 1. And if you have square root of n, 1 over square root of n, then it diverges, goes to infinity, because p is now 1 over 2, which is less than 1. So what happens when p equals to 1? It's the series we already saw, 1 over n, and we know that this goes to infinity. So the p-series test makes sense. And the ratio test, now it becomes a little bit more like a theorem, because now you can apply this test to general type of series. So it says if you compare the ratio of two consecutive terms in your series, depending on that limit, you can determine the convergence and divergence of the series. So if the limit of ratio is less than 1, then the series converge. If it's bigger than 1, it diverges. So if it doesn't tell you about when the limit is equal to 1. If the limit of ratio is equal to 1, you cannot conclude anything about this series by the ratio test. which means that you have to find another way to determine the convergence and divergence. So let's look at this one. This is AN, and let's compute the limit of ratio. So AN plus 1, AN. So if you just plug in the formula, here it's 2n plus 1 factorial, n plus 1 factorial, n plus 1 factorial, and 2n factorial, n factorial, n factorial. And this is same as, let me put it here, 2n plus 2, 2n plus 1, n square. So it's 4, bigger than 1. Therefore, it diverges. Okay? So I'm going fast because some people may already seen this content in your engineering mathematics, or if you didn't, probably you can go back after the class, because it's not that hard. So you can just go back to your video, whatever slide, to review what I've just said. So let's talk about the root test. If your sequence can pass can be applied to the root test condition, then you can determine the convergence and divergence of your series. So it says if you take the nth root of your summand and then take the limit, depending on the limit, if it's less than 1, it converges, bigger than 1, diverges. So let's look at this example. So your AN is 1 minus 1 over n to the power of n squared. Let's take the limit of nth root. It's already positive number, so I don't have to take the absolute value. So it's the limit of 1 minus 1 over n to the power of n. So what is it? Anyone have idea what this is? E, but you have a minus here. So you can consider this as a minus on top of n here. So it's e to the minus 1. So this minus 1 goes to the exponent of e. Okay, so it's a 1 over e. So we'll talk about this in detail when we move to the next slide. We have to define our exponential function. The way we define exponential function is actually using this limit. So this is the definition of the exponential function. So anyway, you can apply whatever method you already know to find out the same limit. Anyway, this is less than 1, so which means that this series converges. Okay, so here are our limit comparison test and other tests. So I want you to just get the idea, not the detail first. So first get the idea, detail is next. Idea of a limit comparison test is that you want to compare two series, and if the series behaves the same, then you can conclude the convergence and divergence of one series based on the information about the convergence and divergence of the other series. So the conclusion is I want to say something about the series A. So condition is if they have the same ratio, if the summands have this ratio which is bigger than or equal to 0, so let's say just bigger than 0, then this series A behaves the same as series B. So if series B converges, then A converges. And the same thing for divergence. If the limit is bigger than 0, then if series B diverges, same for the series A. It's only when the situation gets a little bit different when you have a limit equals to 0, so it has a equal sign here. What happens is the term AN decreases to 0 way faster than term B, right? So that means the series A converges way faster than the series B. So that's why you can throw in the equality sign on this condition, but you cannot throw in equal sign here. So if B diverges, then even if your limit A over B equals to 0, you cannot conclude AN diverges, because you can imagine that AN decreases to 0 way faster than BN, but it doesn't mean that AN converges, because AN could diverge way slower than the series B. It only tells you AN progresses way slower. Series A progresses way slower than the series B, but doesn't tell you anything about convergence or divergence. So you shouldn't throw in the equality sign here. So for example, in this case, you can compare. So this is the series A, and you can compare it with the series B of this type, and using the limit comparison test. Since this one converges, you can conclude that this one also converges. In some sense, these two series behaves the same. And the comparison test is the last test you might want to apply, because this is the hardest one. And it also about the convergence and divergence of series A. So depending on the convergence and divergence of series B and the size of each summand, if the Bn is always greater than An and all of those terms are positive, and if the series B converges, then you can conclude series A converges. So in some sense, since Bn is always bigger than An, if Bn converges, the series A, it must be smaller than series B, so therefore series A must converge. Right? That makes sense. And if you have an opposite inequality, let's say Bn is always bigger than An is always bigger than Bn, and if you know that the smaller one diverges, then you can conclude that bigger one also diverges. So that's why this makes sense. And you can apply this to 1 over n factorial to conclude that it converges. In a sense, what it means is that this is your An, and you want to find Bn, whatever that is, whose series converges. Then you can conclude that your series A also converge. Okay, so that's pretty much it. Before we move on to the next slide, I want to take any question if you have. Do you have a question?
Which test we should use in which cases? How to determine which?
Well, if you find anything works, that's the test you have to apply. There's no rule. So basically, you have to. It's better to follow the order that I laid out here. So you first take the nth term test, but nth term test is not about convergence. It just tells you about the divergence. If it doesn't pass this test, then you don't have to move on, because it diverges already. And then you look at the series, whether it's alternating series or not, and then you see whether it's a geometric series or not, whether it's a p series or not. If anything if anything not applied, then you can take the ratio test and then nth root test and limit comparison. And the last one you might want to apply is the comparison test.
For one series, gonna be able to conclude we can use two tests.
Yeah, you can. Yeah, you can apply. I mean, two different tests can be applied to the same series. Oh, yeah. All right. So if there's no other question, then let's look at the next one. So where is the paper right now? Can I track the paper? Okay. And did anyone wrote your name in the paper? Are you guys wrote your name? Okay, so move your paper to here. So anyone in this side, is there anyone who didn't write your name yet? Okay, so raise your hand if you didn't write your name on this side. Okay. So pass the paper to the person who didn't write your name. All right. So and then after you wrote your name, give the paper to this side. Okay. Okay, so let's talk about the second project. So it's about the calculator. So I think this project should be introduced first before the CAPTCHA project because this is more basic than the CAPTCHA. So we're going to make a calculator based on simple arithmetics, plus, minus, multiple, and division. In order to implement basic functions such as exponential function and logarithmic function, we need to understand how power series works. So let me introduce a power series. So power series is a special series of this form. So what are the components to make a power series? So you need a coefficient, you need a variable x, and you need centers c. And the index n start from 0 and goes up to infinity, and it goes to the power and the index of this coefficient. Okay, so there are the components of power series. So whenever you discuss about power series, you can put any number in the place of x, but depending on the size of your value x, this may not converge because it's a series. You don't always have a number. So in order to consider this as a function, you should know the range of x that this power series converge. So it's called the radius convergence. How far can you move your point x from the center C? So if your point lies in the range of R at the center C, then the series converge. And if you go outside of this radius, then the series diverges. Then this R is called the radius of convergence. So this means that if C is here, you can put your value of x only in this range where the radius is R. So outside here, series diverges. So there's no meaning of putting x value outside this range. So let's talk about this example. So first, I want to define this as a function, as I did in here in the Python code. But in order to do this, I need to restrict my domain of my value x. I cannot put any number x because if I put large value, then this might diverge. So let's find out the range of x that I can put it into this function. So I want this thing converge. Let's use the ratio test as if this whole thing is one big sequence. Ratio test says if this is less than 1, it converges. If it's bigger than 1, diverges. So this ratio is same as x minus 1 to the power of n plus 1 to n plus 1 divided by x minus 1 n to n. So this is same as x minus 1 over 2. So I want this to be less than 1 in order to have convergence. If it's bigger than 1, diverges. So when does it converge? It converges when x minus 1 is less than 2. And if it's bigger than 2, it diverges. So I can move my point x from center 1 up to 2 or minus 2. So it's 3. So if I have x value from minus 1 to 3, in between minus 1 and 3, not including the boundary, then I can have a convergence sequence, a convergence series, so I can define it as a function. But if I have x value outside this interval, then I don't have a value, so my function doesn't take any value outside. So So here's the code. So let me put this way. So I want to explain in more detail. So I want to define a function having value n from 1 to infinity, 2 to the n, x minus 1. So if I write it into longer form, so it's x minus 1 over 2, x minus 1 over 2 square, x minus 1 over 2 cube, and so on. Okay? So the flow of my function works this way. So here's the input. If I take the input, what I have to do first is to check whether this input lies in between minus 1 and 3. So check if x lies in between minus 1 and 3. So if it's not, what should I do? The function f of x is not defined outside of this range. So we have to return none. So none is abbreviation for not a number. So I have to return something, but I cannot return a value, because if I return 0, representing that, meaning that doesn't have any value, but sometimes 0 is a value, so people might consider the function has a value 0. So I cannot return a number. Luckily, the float type has a non-type, so it means that it's a float data type, but does not represent any number. But if x lies between minus 1 and 3, I have to compute this series. Now, the problem is it's an infinite series, but I cannot take infinitely many number and add this infinitely many times. So I have to stop at some point. Where should I stop? So my goal is compute this whatever, this thing, but this is the problem here. How can I do this? So obviously I cannot do infinite sum, so I have to approximate this sum with the finite sum. Let's say for some large n. So now another problem is, what will be my large n? What is it? 64? Okay. You can put a large number that you can think of. That's one way to go. And sometimes if you put a large number, just by guessing, this might be enough. Sometimes you don't need that much number of sum end. Or sometimes your number that you thought it was big enough, it's not big enough to get an accurate number, accurate result. So what you have to look for, so there's one way. So let me lay out for you. So how to determine n. So n is the number of iteration. Anyway, so when you sum this over, we're going to iterate many times, n times. But the question is, how to determine n? Same as how to determine the end condition. How to make a condition for termination of the iteration. Okay, so one way you can go is pick large n, such as what you said, it's 2 to the power of 64. Maybe it's too big, I think. Anyway, so that's the biggest number you can actually implement here. So anyway, another method is, let's say, what other method you can think of? So purpose of doing this, purpose of finding or computing the partial sum is to get as accurate number as possible, right? So if your partial sum reached at certain level of accuracy, you don't have to add more summands, right? You can terminate when your partial sum has has sufficient accuracy, right? So check the accuracy here of the partial sum, and if it's sufficiently accurate, then terminate the iteration. So there are two ways. So and then once you finish your iteration, you can just return the result as the result of partial sum as the approximate value of your infinite power series. Okay. So keep that in mind, and then let's try to. So let's try to make this code together. So this is our collab today. So the function that I'm going to implement here start from so this is our series, right? So I'm going to define a function called f. So this is going to be the way you define a function in Python. As I mentioned, I should have put this project as a first project. So if you struggled through the first project, the CAPTCHA project, by reading the script, then you can start over from here. So whenever you want to define a function in Python, basically there are two ways, but one way is using a def keyword. So def space and the name of function and parentheses and name of the input variable, and the colon means that you're starting the definition of a function called f. So this is basic format, but I want to add a little bit more information about the input type and output type. So this is a function that takes the real number and outputs the real number. So I want to take the input as a float value, float data type. So I'm going to indicate my data type for input is a float, and outputs the data with the format of float. So this is not mandatory. It's just indication of the data type, but I like this way because it makes easy to read. And what did I say? What the first step to do is check the range of x. If not, x is in the range of -1 and 3, then you return none. So there is a way you can make a non-type. Simply convert non-string into float. Python automatically makes the non-type data using this command. So when this happens, it returns. So the function terminates by returning this data. But if it's not, then you have to compute the value. So here, so I'm going to return the sum. Sum is my final value. And term is this term. So x minus 1 over 2 to the power of n. So terms start from 1. Okay. So I'm going to iterate until my term equals 0. So it's the same thing as while not term equals to 0. Maybe if it's better for you to understand, you can write this way. So it means that iterates over when the term is not 0. Okay? Term is not 0 means that you have non-zero value to add, right? Therefore, you have to add it. If you don't add, something is not 0, then you're missing some value, right? So you're going to iterate over and over until your term that's going to add it to the sum is 0. All right, so sum, so what I'm going to do is I'm going to update my term to be the previous term multiplied with x minus 1 over 2. So it's because n is starting from 1. So the first term that I'm going to add to the sum is the x minus 1 over 2. So term is initialized as 1. And whenever the iteration starts, it is multiplied by x minus 1 over 2. So I'm going to add that term to the sum. So and then next time the iteration begins, I'm going to use the same term, which is x minus 1 over 2, and then multiply this again to make it squared, and then add it to the sum, and keep doing it over and over. Okay, so when does it stop? It stops when term is equals to 0. So when it stops, it returns sum and finish it. So I'm going to run this code block. So it doesn't returns any output because it's only the definition of function. Let me open a new code block and then test out whether it works fine. So I'm going to print a f of 0. It says it's minus 0.3333. Basically, I think it's minus 1 over 3. And let's try f of 1. It's 0. Of course, it's 0. How about 2? 1. Okay. So it gives me a nice value. So here's the question. Try to do this, and then why does it make sense? Why could I put this as a terminating condition for the iteration? You might think it's weird because the term is always this x minus 1 over 2 to the power of n. So unless x is 1, it never gets 0, right? So here, if I put x equals to 2, it's 1 over 2, 1 over 2 to the power of n. No matter how big n is, this is not 0. So you might think that this never achieved. But however, somehow the iteration is finished so that I get the answer in less than 1 second, right? Why does it work? Why does it make sense? So try this code out. Write this code in your computer and then make sure that it works, and then discuss why this works, why this condition part works. So you can talk to your friends next to you. Where can I track the paper? Where's the paper right now? You guys wrote your name yet? Not yet? Okay. You can talk to your friends next to you. What's the problem? Oh, you want to write the formula in the text block.
There's no.
I'm going to upload after the class.
What we have to discuss now?
You have to discuss why this conditional part after while works. Why that works. Why that term equals to 0 works. Hmm? Do you have a question? Okay. Doesn't work, right?
Yes.
Takes a long time. So it's time to bring your discussion in the group. Okay, so which part? You want to make it bigger? Is that better? Okay. I think this one, it's not the best condition. So this one looks better. This one is not. Okay, make it into a group discussion. So the person on the first column is the leader. So you have to make sure that everyone participate in the discussion. You can pass to, did you write your name?
Yes, I'm right.
Okay. So anyone who didn't write the name yet, raise your hand if you didn't write your name. You didn't? Okay, so I'm going to ask about, maybe you guys were talking something. So how about group 3? Can you tell me about why this works? Who's the leader? You want to see the group 3? Yoon Kyung-un? Okay, so you're the leader. Okay. It's okay to say in English with some errors, but try speak in English. Okay, so
나머지 비트가 이제 비트랑 이쪽으로 이제 분사값 처리하는 걸로 되는데 그래서 그것 때문에 이제 정확하게 너무 작은 값은 스토리를 리스트로 표현할 수 없는 너무 작은 값은 일부러 분사하게 되는 거죠. 너무 많이 나눠지면 이게 F1, F2 개발했을 때 첫째 조건을 붙여서 여기가
Okay. So basically, so you need to understand this is not an ideal real number. What you are dealing with is the float type data. Okay, so whenever you try to compute anything, this is very important because even though we are talking about math, even if you cannot manipulate the data, then there's no meaning of it, understanding the math theory, because every math theory is going to be manifest in a data type. Okay, so term and zero are both float type data. You're comparing this float type data. It says simply that these two float type data are equal. So, but zero is our constant. Term is changing. The variable term is going to be decrease up to zero, right? So if it's in sufficiently small, then it's out of the range that this float type data can handle. Okay, float type data has a certain range of the real number that they can distinguish to get each other. So if it's too small, then the number that you represent as a small number is indistinguishable with the data type that represents zero. So basically, it's the same as zero. That's why this works. So you're going to, what this happens is, if your term that you updated here is going to be as a data equal to zero, then there's no meaning of adding this zero onto the sum because it's not going to change anything, right? So if you keep adding zero after this point, so therefore that's the where you have to stop. Okay. The problem is, okay, so it's a small number that this condition, if you want this condition to be fail, the problem is that if your value x is closer and closer to -1 or 3, then you need more and more iteration to get this condition. Okay, so it's unavoidable. If you have x closer to 3, then the rate of the term that is decreasing to 0, it's getting slower and slower. So you need lots of more iteration in order to have this condition. So if you want a little bit more efficient, but gets less accuracy, but doesn't really matter, then you can put an extra information about, let's say, I want to consider whatever value less than 10 to the minus 15 as 0. So if your term is in between these minus epsilon and epsilon, then instead of comparing as a float type data, you can compare this non-zero value with the term here. So then you can just consider it, okay, so if I get the term whose absolute value is less than 10 to the minus 15, then it only changes the 15th decimal point of my calculation. So really doesn't matter if I want to see the first 5 or 6 decimal point of the result. So I'm going to stop there. So in that case, you can get a little bit more efficient algorithm to compute your function. but really it's up to you. Okay, so any other questions you want to discuss about this? Okay. So let's look at other. Okay, so now we are going to actually implement functions. So arithmetics, or plus, minus, multiple, division, can be done by simple symbols. As Python already have those kind of arithmetic. But I want to implement functions like exponential function, square root function, which you are looking at right now, and also logarithmic function and sine and cosine. So let's start from square root. So how do I compute the square root of x? There are many ways to compute this. One way is to use sequence. So let's think about the sequence for a moment. So if you define a sequence with this recurrence relation, then you always end up getting a limit which is equals to square root of x. So how do you compute? How do you find the limit? How do you find the limit? So it's the same problem. We cannot compute it for infinitely many n. So we have to find where to stop, right? So basic strategy is the same. So if you want to find the square root function, so here's your input. The first thing you need to do is check whether your input is negative number or positive. If it's not, then you get a negative number. So it doesn't make sense. You cannot take a square root of negative number. So you return the non-value, return none. So if it's yes, then you have to compute an satisfying an plus 1 equals to 1 over 2 an x over an. Okay? So the question is when to stop. The same question here. So you can take a big N, set it as a constant, but it's better to make it a little bit efficient. Just take an and an plus 1 and compare these two values. If you see no difference between an and an plus 1, then it's where you have to stop, right? There's no update anymore. Then that's going to be your square root or the limit. So let's implement this way. So here I'm going to define square root x. So x is going to be the float type and outputs the float. So if not x is bigger than or equals to 0, or actually if you have or maybe this way. So if x is 0, less than 0, then you can return none. And if x equals to 0, then you don't even have to compute. Return 0. Right? So if any of these conditions are met, then now you have to compute your sequence by the recurrence relation. So I'm going to set a and b as 0 and 1 for the first time. So a for an and b for an plus 1. Okay. And I'm going to iterate over and over until I have same value for a and b. So that means an and an plus 1 are equal. Okay. And I'm going to update my AB by this. So B plus X over B divided by 2. So when you put the equal sign between the pair of values, then what happens in Python is you compute everything on the right and then replace that value to the left. Okay, so A will be replaced by B, but at the same time, B will be replaced by B plus X over B over 2. That means it's the next value of B. Okay, so A is an, so it's replaced by an plus 1, and B is an plus 1, it's replaced by this value, which represents an plus 2. So after each iteration, I keep updating AB from an plus 1 to an plus 1, an plus 2. Okay? So I'm going to stop the iteration whenever I see these two A and B are the same, because now I don't have to do any more iteration. So let's run this once, and then, so we have to make sure that you run this code block once so that this information is stored in the memory. And then let's print out some function value. Let's say I want to compute square root of 2. Now it's done here. I can do the same for, let's say, about 4, 2.1, 2.0, right? I think it's working. And the same reason, now, if you want to if you want to iterate the iteration until this is true, then it's the best way, this is the way you can get the best accuracy. But however, this is not the most efficient way of doing it. So whenever you see the difference of A and B less than some certain value, then you might want to stop, because after that point, the decimal points may not be as accurate as the best possible accuracy, but it's enough, because most of the times we don't need more than like 6 or 7 decimal point, right? Okay, so raise your hand if you have any questions. So I'm going to let you do it by yourself or in a group. So let's try to, so what we have done so far, so this f is just an example, and we define this square root, and let's try to define exponential function. Okay. So here's the definition of exponential function. It's the limit of n goes to infinity. So by the way, if you want to put the math text, you have to use the LaTeX command. So I'm going to share this page. So if you want to look up what's the command for writing the math formula, you can look up my code on the web later. So here I'm going to take left 1 plus, sorry, so here 1 plus 1 x over n, the power of n. Okay. So I'm going to use this as definition of my exponential function. Of course, there are other definitions. Let me give another definition here. So you can also define your exponential function as a power series. So 1 plus x plus x squared 2 factorial, x cubed, 3 factorial, and so on. So you can use either way of defining exponential function. Okay, so try to define your exponential function here, and then let's try to define sine and cosine. First sine, and then next cosine. So you have to write something on below sine and cosine, but let me give you the definition of sine and cosine. It's not a definition, by the way. So sine and cosine and sine are defined to be the x and y coordinate of the point on the unit circle boundary, right? But in order to compute, this is the best way you can compute sine and cosine. Okay, so here is one code. Cosine is 1 minus x squared, 2 factorial, x fourth, 4 factorial. It's already in the slide, but I'm just giving you the information how to write a text math formula in Jupyter Notebook style. So you can use this series, power series, to define sine and cosine. Okay. So I'll give you about 10 minutes to write your code here. So if you have any question, let me know. I'll walk around to see if you're doing. Maybe I can share it if you want to see it right now. Okay, so I'm going to share this here. So if you want to see the code on your computer, you can go to the Notion site. I just linked my notebook here. So you can see the formula here, or you can go to the slide, whatever you want. So try to implement sine and cosine. That's going to be the part of our project, the calculator project. Where is the paper? Can I see the paper? Anyone who didn't write your name yet? Okay, so everyone is here. Any question?
모르겠어요.
Which part?
지금 저 사인이랑 사인 저렇게 만들라는 거 코드 있다는 거 아니에요?
Yes.
잘 몰라서 좀 그냥 들려주세요.
But this one is implementation of this symbol, this formula. So you might want to this one. So this is the implementation of power series. So sine and cosine can be computed by power series. So your code will look more like this. Yes.
Last PPT.
Yes.
Example is when n
Goes to 1. Right. Minus 1.
this condition is not.
Well, but you can get rid of the first term. Consider this is, taking the rest of the terms except the first one
Yeah.
is always positive, right? So
We 이렇게 이거를 지금 AN이라고 했을 때.
right.
근데 지금 여기는 AN은 0보다 커하니까.
Then you can take an to be start from the second terms. What matters is the rest of the infinite terms that determines the convergence and divergence. No matter what you do on the finite first terms, doesn't matter. The convergence and divergence is not affected by the first finite terms. So you take away the first finite terms and consider this an is starting from n equals to 2. Then you can apply the limit comparison test. Anyone have a question? Okay, now start discuss about your implementation or your question in the group. So it's very important that you have to talk to your partner or anyone else, because if you speak whatever you think or don't know about, then you'll get that's the starting point where you start to understand. Okay, so talk to your friends next to you. Talk to your friend right next to you. Show your code to your friends and share your ideas, share your questions.
민수.
Okay. Is anyone here? No? Oh, you're in different group? Same group, 8? Oh, come here.
One question.
Yes.
Like, sum is equal to will be 0 because in the first term.
Yes.
The term is equal to 0. Yes.
But if a term is 0, then it will be always 0 if you multiply something on 0.
So that's why our term will be this one. Yes. Because
Sine x?
we have to add like for sum every time term. That's why.
No, why you put the sine x here?
No. What should be our term? I don't know.
1?
Why?
Why? Because the term is keep multiplied by something. So the first time, so here is a sine. Okay, so first time you have to add is 1.
Yes.
Okay? The next term you will add 1 times of something.
Ah.
And the next term you add is the current term the first term, multiply to the something to get the second term. So it always start from 1.
Question. While not our term will be like it's bigger than minus minus
Well, no,
1.
that's too big. I mean, everything will fall into this range because term is going to be decreased fast to 0.
We should use this one again.
So it's a small number. Just EPS is small number, 10 to the minus 15.
This one also should.
Right. So, and you have to define what EPS.
What?
Oh, EPS.
And
Oh, you already have EPS, right? So,
And then
okay.
일단 이렇게 만들어보는. 아니요, 죄송합니다. 파이썬으로 다시 만들게요.
What is it?
C++로.
It's okay.
일단은 맞게 나오긴 해요.
첫 번째는
팩토리얼 함수 정의하고 뭐 제기 돌려가지고 팩토리얼 통값 보내고 했어요.
Okay. I know you're still discussing about this, so I want to discuss one more thing together with whatever you're discussing right now. So here you're looking at the power series whose radius of convergence is infinite. So this series for sine and cosine always increase no matter how big your x is. However, let's say if you want to compute sine of 100, you're not going to input 100 in x because that's going to be very inefficient. So you're going to shift your 100 to be in the range of minus, let's say, pi over pi, or maybe 2 pi over 2 pi, whatever. So then, because of a periodicity of the sine and cosine, you can compute the sine of that number, which lies in between minus pi to pi. Instead of putting 100, you can put that small number to get more accurate number. I mean, you can, so that you get accurate number of sine 100 more efficiently, right? So you can simply implement these power series, but put a little bit more extra lines so that your code works efficiently, okay? So using the periodicity of sine. 파이?
네. 파이분의 2 해야 되는 거 아니에요? 그러니까
파이분의
이렇게 그러니까 정확도 높이려고 하는 거잖아요. 지금.
yes.
이렇게 여기서 그럼 마이너스 2분의 파이부터 파이부터
마이너스 파이 to 파이.
파이까지인데
Yes.
그러면은 파이를 써야 되는데 어떻게 써요? 그러니까 함수에서 못 쓰지 않나요?
So you can use constant pi defined in numpy package, or
근데 너 파이를
if you,
쓰면 안 돼.
or it's best way just put the constant pi defined somewhere else. Just make pi number. So that's way actually the numpy defines its pi constant. So put the pi in a really long decimal point. Then that's going to be as accurate as ever. The best, it's going to be the best accuracy if you just put the large decimal numbers of pi.
길게 써서
Yes, that's the only way.
너무 파이 하는 게 예쁘겠다 그래서
No, I think it's better to put the pi constant on
그냥
top of,
여기다가요?
outside of the definition.
위에다가
In the, yes,
네
let's say pi,
해서
right.
정리하고
Okay, so do you want to do it together or you want to move on? So it's your choice. So if we move on, we can start to make the calculator for the second project. Or if you want to do it together, then we can pick one of these three functions, exponential, sine, cosine, or there are one more function we need to implement, the log function. So we can pick one of these four functions to implement together. So which one do you want to do it here? Want to move on or do it together? Okay, I think you guys are kind of working, so I don't want to spoil your work. So I'm going to leave this implementation as your assignment. So let's try to think about how to implement log of x. So this one also takes the float type and outputs the float data type. We're not going to use the power function here. So we're going to use the definition of log. So definition of log is the inverse, so it's the inverse of exponential. Log of x is inverse of x, right? So that means if you want to find log of 1, you need to find the value whose exponential is 1, right? So you have to go the opposite direction. The way you can do it, in this case, actually it's about finding solution of an equation, is using a bisection method. So let me go through what the bisection method does. So here, I'm going to write something here. Right, so here we have exponential function y equals to x of x. Okay. So we have to start from the exponential function. You want to find log of c. Let's say log of d. Okay. So if you want to find the log of d, that means I want to find this value c, which is the x coordinate of the cross point of this graph of exponential function and y equals to d, right? I want to find the c where x pub c equals to d. So how do I do that? So bisection methods allows you to find a solution or root of an equation. So first you have to start from, it's not applied to any cases. In this case, it applies well because the exponential function is an increasing function. So first, you should start from the domain or interval, which is big enough that contains this c. So we don't know what c is, but we know what d is, okay? So we know, but we don't know. Okay? So so we will talk about how to determine the initial interval that must contain the c. Even though c is not known, there is a way we can determine the interval a0 to b0. So assuming that we know this interval to start with, what we have to do is compute the value at the endpoints f of a0 and f of b0, and then compute the value at the middle. So in this case, let's see, middle point is 0. So this is my c0. Okay. So here f of c0. I'm going to decrease the size of my interval into half. So I'm going to choose which half of my interval contains the value of function. So I compute and compare these four values. This one, let's see. This one, this one, this one, and D. So if D lies in between FC0 and FB0, where like this one, then I keep this interval, and get rid of the rest of the interval. So I start over with this interval, saying that now this is A1 and this is B1. And then we do the same thing again. So now middle points is C1, and I'm comparing these four values now, FC1. So in this case, this is same as FA1, and this is same as FB1. So comparing FA1, FC1, FB1 with the D again, now I have to choose which half of my interval to keep and get rid of the other. So in this case, I can keep this part because D lies in between here. So I keep this one. So my C1 becomes A2 for the second interval. Now B0, B1 equals to B2 again. So if I keep doing this, I make my interval smaller and smaller. Each time it gets just half of its original length, and it's going to be, it decreases fast, it decreases exponentially. And then at a certain point, my interval is short enough so that there's no difference of the function value at the left end and the right end. That means whichever value I choose, I can imagine that this is going to be the c, which gives my value d when I compute the function x. So this is called the bisection method. So we are going to implement this as a function log. Now, first step, find in the interval minus n to n that contains x. So here, x is an input, but it serves as value d in our picture I just draw. So, and then the second step is use the bisection. To approximate log of x. So that's going to be the value c I just draw in the picture. So how do you find first the interval minus n to n, which contains, so this is actually the interval that x lies in x pub minus n to x pub n. Okay, so minus n to n is the interval for the x log of x, but no, it's confusing because I used the x as a name for the variable of input of log. But anyway, this is the minus n to n is the interval for the exponential function that I'm going to start with at the beginning. And then I want to check whether my value x, which is the value of exponential, must lies in this interval, which is the value of the y coordinate in the graph of y equals to x pub x. Okay, so and then we're doing the bisection method. So I'm going to start with n equals to 1. So I'm going to repeat increasing the n until I get the result. So if x of minus n, x of n, if x is not in this range, I keep increasing my n so that this minus n to n contains the desired point, the log of x. But if I increase by 1, this might take forever. So I'm going to increase by twice. Like I'm going to double it after each time. So once I did it, I'm going to set my interval, left end bound right end as a and b. And we start from minus n to n. By the way, so the c, the center is automatically becomes 0. So I'm going to iterate until, so this is, this should goes after this comment. Right. So I'm going to iterate until my left end and right end are indistinguishable. So you can, as I said, make it more efficient by setting the EPS variable. But anyway, all right. Well, I don't think I have to define C here because I will compute my middle point anyway. So if the exponential of C is less than X, I'm going to replace my left end to C. And if it's not, then I'm going to replace my right end to the middle point. Okay. So once it's done, then I'm going to return C. So it's after the left end and right end of my interval is indistinguishable. So you can take either A or B or C, whichever value, as your log of X. Okay. So I'm going to run this code, and then let's test out log of 2. Where is the... Oh, XP is not defined. I didn't define XPS. Okay, so for now, just because I don't want to go over this again, I'm going to just cheat a little bit, just to use an npi x, okay? And then, okay, run this again. And then let's print this out. It takes a while because I put the terminating condition like this one. I think it's taking too much. So I think it's okay. So until 2, is it right? So let me check. Here. Okay, that works. I think it takes too much time here. So I think I have to use EPS constant. Okay. So if it's not AB is less than or equal to this, then I keep doing iteration. So I want to keep the iteration until this A minus B has absolute value less than epsilon. So now you got answer here. So it's 0.69 something here. So it's accurate as 15 decimal point. So you can read this one, sorry, pretty accurate here. So this is how you can define a log. And we can discuss how, there's another way of defining log using power series. I put it in the slide. You can do that, of course, too. This is one way you can do it. All right, so, okay, I said that you're going to implement on your own for the sign. So let me cheat again. So I'm not expecting you to do the same here because all the point of doing the second project is you have to implement sine and cosine of your own, not importing from the other extra outside package. But here, I don't want to spend time writing the code, so I just cheat it here. So log is here, and okay. So let's try to think about how we can make a calculator. So this is one way you can do the project. You can make another way of doing it. So my idea of making a calculator is something similar to your the engineering calculator. So if you see the engineering calculator, sometimes there is a window that you can actually type in the command, but I'm thinking of more low level engineering calculator. But for example, if you look at the calculator like this, let me show you this one, like this one. So it only shows you the numbers on the screen, and you can type in numbers, and then you press some buttons like the square root button like this one. Then it computes the square root of the number that you just typed in, which appears on the screen. And I'm assuming that you have some more buttons extra, such as sine, cosine, or exponential and log. But instead of making it into graphical interface, I'm just using a text-based interface. So if you type in the text, such as sine or cosine, then this program will calculate the sine and cosine value of the number that you previously input. So that's the basic idea of my calculator program. So I'm going to walk through the basic code that I laid out in the slide. So here's a basic code. So here's sine and cosine. So basically, my calculator is going to run forever. So it's going to repeat forever until I have a special command to exit my program. So this will continue forever, which means it will iterate forever. And there is a exception when it breaks. So if the text exit is typed in, then I want to break the loop and then terminate the program. So except that, I always have iteration. So what is the iteration here? I want to take the input from the user with the text. So I take the input by input text, input command like this, and then store whatever the string that I put it here. And depending on whether the expression that user typed in is a number or string, I do different. So try to convert my expression into a float value and then store it to val here. If if the expression is not a number string, if it's not a string that represents a number, then it will raise a type error or a value error like this. But it will not immediately raise an error. It's only after I put it into try and accept command keywords here. So try and accept literally try something and then collects exception here. So I try to convert my expression as a float, and if that raise a value error, meaning that the expression is not an expression of a number, then I do something here. That means I typed in some function. So I'm expecting typing either number string or function string. So if the expression is exit, then I break. But if it's not, then I search for all the possible input name of the function. And if one of the string matches with the name of function, then I compute the value of that function. So that's what this for does here. And I also want to type in, user could type in plus, minus, asterisk for multiplication and division symbol for this type of expression. But anyway, whenever my arithmetic symbols are inputted, that means I need to take another number as an input, right? So if that happens, if arithmetic expressions are put it into the program, then I want to take another input as a value, and I want to compute the arithmetic operation between two inputted number, the previous one and current one, and then store that value here. And then whenever I did computing all the values here, then I will update that value to the current value string as value variable here, and I'm going to print that value as same as the calculator. So I'm going to give you a brief idea how it looked like. So I'm going to define it, right? Short version of this. So I'm going to take the input, and then I'm going to print the output. Oh, by the way, so I need an exception that breaks the loop. So if the expression is exit, then I'm going to break. But except that, I'm going to print the expression I just inputted it here, and then keep iterating over and over. So I'm not sure whether it works. Oh, it works here. So if I run this code, this is not a calculator. I'm just showing you how this generally works. So let's say I input 1. So it's going to output 1, the same expression. So if I input sign, then it just outputs the same string that I just inputted. But if I put exit here, then it terminates the program because it meets the condition of this line, and it says breaks the loop. So it's terminating. So basically, I need to put something more in between here, so that makes it into calculator. Of course, I need to use all the functions that we defined previously, and we're going to introduce efficient way of searching the character and strings that matches with the name of the function we defined previously using the dict type of the Python. Okay, so other than that, we're going to do it together next time. And if you have any question, let me know after class. And okay, so I need to talk something about this group. Okay, I can see, again, as you can see, many people are trying to do the CAPTCHA or calculator, the first two projects. It's perfectly fine, although I might have to say, if many groups are doing the same project, then obviously there are some groups that are better and some groups that are, need improvement. So you have to take that in consideration when you're choosing your group or topic. And there are a few people wants to do the third one and fourth one. So if you don't have a group yet for the first two topics, then you might consider moving yourself to the third and fourth topic, because those topics are also perfectly interesting. So I'm not going to finalize a group or make a group right now. I'm going to ask again on Friday which topic you want to do for the first project. So if you change your mind, you can wipe your name out and then put your name again in different place. So think about the topics again. We'll talk in Friday again.